Warning, the video you're about to watch contains mathematics at the level of integral calculus, also known as Calc 2. All material has an assumed prerequisite of differential calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for Calc 2 students or integral calculus students who are going through a section on how to evaluate integrals involving trig functions. And this one specifically was a nightmare for me when I was a student. It is actually a very awesome integral, but you do have to kind of know how to derive it. So let's go ahead and go through and derive this integral itself. So far, if you're going through Calc 2 and you're learning it in the order that I teach my students, which is you learn by parts, well, technically you learn how to integrate, then you learn how to do U-substitutions, then you learn a little bit about how to use geometry to help you evaluate to help you evaluate integrals quickly. And then you go into by parts methods, and then you step into this material. Then you have a limited list of tactics. One would be direct integration. And that is just, do you know the antiderivative offhand? And if so, then write that as the answer. Well, we don't know the antiderivative of secant cubed offhand. Let's just pretend. And so I'm going to cross that tactic out. The next tactic you learn is U-substitution. And in this case, I really do believe U-substitution is going to be somewhat helpful. One thing you need to note is to do a U-substitution, you have to be very aware of what to do for your U-sub. In other words, you only have a couple choices really here. I know that I've seen people tackle this problem a lot of different ways, so maybe I'll go ahead and write some of the tactics or some of the approaches I've seen over the years. So one approach would be just to deal with the secant cubed as written. Another approach that I've seen a lot of students use over the years is to rewrite this as 1 over the cosine cubed. Well, the first of those two methods is actually our original integral, so that's not going to be anything special. The second of those methods is attractive only for one reason, because you might think you can do a U-substitution here, but be very careful about this. If you do a U-sub, you're going to let U equal the cosine, and that will imply that du will steal away a negative sine of x dx, and we don't have a negative sine of x to steal away. That does not mean it won't work, it just means it makes it more challenging. So I just divided both sides by a negative sine of x because that's what I'm going to replace dx with. And if you do that substitution, I'm just letting you know it gets really messy. You have this integral 1 over, remember, cosine is u, so this is going to be u cubed. dx is negative, I already put the negative out front, so negative 1 over sine squared, or sine of x, not sine squared, but just sine of x, and then du. And you can't do anything with this, you can't evaluate this right now because you have a mixture of variables. Your integral is supposed to be in terms of u only, and unfortunately you do have u, but you don't have u right here, and that's a problem. Now, often it's the case that you can manipulate this expression by using your relation between u and x. However, if you take a look at that, u is equal to cosine of x, there's really not an efficient way to write sine of x in terms of cosines of x. Some people will say, well, I know that sine squared is equal to 1 minus cosine squared. Well, you're right, but we don't have a sine squared. We have a sine. And then other people will say, yeah, but if I take the square root of both sides, then I have sine of x is equal to plus or minus the square root of 1 minus cosine squared of x. Yeah, you're 100% correct. That is absolutely right. However, that means your integral is no longer an integral function. It's a list of possibilities. You have a positive version of it and a negative version of it. And not only that, but your denominator will have a square root in it along with a u cubed. That's just terrible. It just gets more and more complicated. So when you start going down a road when it comes to integration and things get more and more complex, that's the time when you hit the pause button and you go back and try something else. So going back, let's take a look at these tactics. Well, I said a U-sub might be worthwhile. I still haven't actually tackled the problem yet. Let's go ahead and list out other things before we try a U-sub. Maybe we have better luck listing out other possibilities. Is by parts a possibility? Well, it might be. Remember, when you use integration by parts, you want a piece that you can take the derivative of, and you want a piece that you can integrate. And right now, it looks like we're only dealing with one function, but in reality, you're dealing with two functions. And that is the key to doing this integral. The moment you recognize that you're dealing with secant squared times secant, that's the moment that you should realize this is definitely great for by parts, because you can integrate a piece of it, specifically that yellow highlighted piece, and you can differentiate a piece of it, specifically this blue highlighted piece. Remember, if you're one of my students, when you're choosing what to integrate for the by parts method, you choose to integrate the largest piece you possibly can. And of all this stuff, secant squared and then secant and then dx, the largest piece is the secant squared dx. You can integrate that. You know it's antiderivative. Let's go ahead and write that off to the right-hand side. The piece I'm going to integrate is secant squared of x dx. The piece that I'm going to differentiate is just the secant of x. Let's go ahead and write down the derivative of the secant. That's going to be secant of x, tangent of x, and then dx. It's the differential of u. And then the antiderivative of secant squared is tangent of x. And remember, the by parts method tells us if we're given the integral of u dv, which in this case would be secant times secant squared of x dx, then that can turn into uv minus the integral v du. Let's go ahead and write that down over here. So this is going to be u times v, which is secant of x. Let me highlight that. It's secant of x, tangent of x, and then minus the integral of v du. Well, that would be minus the integral of tangent of x times secant of x times tangent of x times dx. Or in other words, secant times tan squared. Now, a lot of people look at this, and if you're my student, then you've heard me say, if your second integral gets more complex than your original integral, you should probably quit. You're probably doing something wrong. This is an exception. There's always exceptions to those statements. Those are just general rules of thumb. They can be broken, and they do break every once in a while, and here's just a good example of that. When you look at this integral, again, you're faced with a lot of choices. Do you know the antiderivative offhand? The answer is no, you sure don't. Do you know that you can do a U-sub? Actually, you possibly could. But the more I think about it, no, you won't be able to, because if you try to U-sub, for example, you might want to let u equal secant. Well, then the derivative of the secant would steal away a single power of the secant and a single power of the tangent, and you would have an integral of just tangent. And unfortunately, there's no way to write just the tangent in terms of the secant, so that's a bad sub. Well, what if I chose to let u equal the tangent? Well, then du would have to steal a secant squared, and I don't have a secant squared available to steal. I'm not telling you that that U-sub will not work. I'm telling you that if it does work, it's going to be a lot of work. Some very astute students will say something like, hey, what if I write everything in terms of sines and cosines? They're used to this from trigonometry, that everything can be written in terms of sines and cosines. And that is actually true. This can be written in terms of sines and cosines. However, again, a U-sub here, not a good idea. If you let u equal the cosine, it'll steal off a single power off that numerator of the sine, its derivative will, and then we'll have a sine, a single power of sine left over, which is not an even power, and you're locked out. And forget about letting u equal sine, because while its derivative will steal away a power of cosine, it will only steal away a power of cosine if that cosine is in the numerator. So again, a U-substitution here is not a great idea. That brings up a really good point. A lot of students will want to turn everything into sines and cosines, and that is either too much work, too slow, or just won't work. It won't give you anything. So try to let go of that habit. It's not a terrible habit to have, but it's when you're in Calc 2, it doesn't really help you that often. The one thing that will help you is not calculus, but trig. If you remember from your trig, and you remember from the previous video that we did just a few minutes ago, well, I did it a few minutes ago, I recommend before starting a problem, always ask yourself, can I just take the antiderivative, which we cannot do here? If it involves trig functions, is there a trig identity that you can use? And the answer here is yes. Tan squared, that's equal to secant squared minus 1. So I'm going to trade that out for a secant squared minus 1. When you do that, you get down to this more convoluted looking integral. That's okay, because this is going to be the secant times the tangent, and then that last term there, which is an integral, will break into two subintegrals. One of which we happen to know the antiderivative for. If you don't recall, this is one of the ones that generally gets proven at the beginning of a substitution section when you're dealing with trig functions alone. The antiderivative of the secant is the natural log of the absolute value of the secant plus the tangent. Let me go ahead and write that down. So here we are. We got our entire integral kind of set up, but notice our original integral right here is equal to this stuff that involves itself. It involves its own integral. In other words, the integral of secant cubed of x dx is some statement that also involves the integral of secant cubed. Well, recall from your algebra courses, if I told you had x is equal to 5 minus, who cares, like 7 minus x, you would add x to both sides, right? You'd say, oh, that's 2x is equal to -2, and divide by 2, and you get x equal to -1. It's the same idea here. I have the integral of secant cubed on the left-hand side. I have the negative integral of secant cubed on the right-hand side. So I'm going to add the integral of secant cubed to both sides to get rid of that on the right-hand side, and I'll get the following. 2 times the integral of the secant cubed of x dx is equal to the secant times the tangent plus the natural log absolute value of the secant plus the tangent, and then plus some constant of integration. Now that we've run all the integrals, there's just some constant of integration that pops out. Notice I call that c sub 1. It's because I'm going to divide everything by 2 to figure out what the actual integral of secant cubed is. And when I do that, that 2, while it will go in each of these denominators here, it will also bleed into that constant, creating a brand new constant. And notice that constant I don't call c sub 1 anymore, because it's not the same exact constant. It's c sub 1 divided by 2, which I'm calling c. And this is one of the most entertaining, I would say, antiderivatives, the secant cubed. It's also kind of neat to see its value. I'd just like to draw your attention to the fact that this is 1/2 the derivative of the secant plus 1/2 the integral of the secant. That's what the integral of secant cubed ends up being. Half of the derivative of the secant plus half of the integral of the secant, and there'll be a plus c that pops out because you're doing an indefinite integral. All in all, I would say this is a good integral to try to commit to memory, because it does occur quite often, or often enough that you don't want to derive it every single time. There's too many spots where you can kind of lose your footing and forget what you should do next. So it's always nice to remember the integral of secant cubed is just half the derivative of the secant plus half the integral of the secant. Obviously, that requires you to remember that the integral of secant is the natural log absolute value of secant plus tangent. All right, I think that's it for this video. I hope this was helpful for you, and I hope to see you again in a future video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.